Section 9.2, Series and Convergence. Infinite series are sums that involve infinitely many terms. Infinite series play a fundamental role in both mathematics and science. They are used to approximate trigonometric functions and logarithms, to solve differential equations, to evaluate different integrals, to create new functions, and to construct mathematical models of physical laws. An infinite series converges if its sequence of partial sums converges. Many infinite series, even ones known to converge, are difficult to evaluate exactly. The problem of estimating their limits arises naturally. Technology proves useful both for calculating partial sums and for estimating the error committed in using partial sums to approximate series. If we add the terms of an infinite sequence, remember sequences separated by commas, we get an infinite series, or just a series as we call it. And it is denoted the sum of n terms, as n goes from 1 to infinity, of our sequence is the first term plus the second term plus the third term, all the way up to the nth term, where A1, A2, and A3, and so forth are called the terms of the series. To find the partial sum, we consider the sequence of partial sums. If the sequence of partial sums converges to some number s, then the series converges. The limit s is called the sum of the series. If the sequence of partial sums diverges, then the series diverges. Find the sum of the first 5 terms of 1 plus 1/2 plus 1/3 plus ... plus 1 over n plus ... by using the sum command on your calculator. So on your screen display, it is going to look like this. Now let's look at how we enter it. Okay. Here is my display, but I'm going to do it with you. F3, there is sum. This is a function of x in this problem, 1 divided by x, comma, tell the calculator it is x, comma, from 1 to 5. It's going to give me the sum of the first 5 terms of the series. There it is. Now, if I wanted to have a display of what the first 5 terms were, I would type in sequence. I can do that 2 ways. I can go to S and up arrow until I get to sequence, SEQ. There it is. And to use sequence, I need an expression and a variable and the low and the high. So I have to tell it how many terms I want. And my sequence was once again 1 divided by x. The variable was x, and I wanted the first 5 terms. And it will list those terms for you. Just a little something for you to know. Do we think that series converges? So we're going to put our calculator now in parametric mode. Remember that that is found right here under mode, and we're going to go to parametric. Hit enter and hit it again. It'll say pair down here. Then we are going to go into our calculator, and we are going to let x equal t, y be the sum of the sequence. Now this time we have to actually type in sum, the word sum of the sequence. In our window, we're going to let the t minimum be 1, the maximum be 20. My t step is 1, x minimum -1, max 20, scale is 1, y minimum -1, y maximum 5, scale 1. So when I go to my y equals menu, you can see there's my x of 1 equals t. Don't forget you have a button for t right here. Okay. So it's got to be a function of t. And then y1 is the sum of the sequence. When you type that in, you can actually just use your alpha to type sum, parentheses, and then you can use that command for sequence. And again, it's going to be 1 over t, comma 1 to t. Then it says, so I've entered that, it's up in my display. I'm going to go to my window, let your t minimum be 1. That's the first number we're going to enter, 1. T max 20. All right, T step is 1, meaning that my T's are going to increase by 1. My X minimum is, my window for my X is -1 to 20, scale of 1. My window for my Y is 1 to 5, scale of 1. Oh, I forgot to say this. Go back to, while you're here, do second 6 and put it in dot form. Okay? Enter and enter. Now, we're going to look at the graph. And if we watch it, I'm going to regraph it. Okay? And you can see those dots. Now, it says here in the book to trace it. Trace is right here. I don't normally trace, but we're tracing term by term. Look at that. My first x, 1 over 1 is 1. Hit the right arrow. We're graphing a series, so that's adding up the terms. So 1 plus 1/2 is 3/2. Now the next term would be 1/3, okay, 1 over n, so we're going to add 1/3 to 3/2. And then we're going to add 1/4 to that. And then we're going to add 1/5 to that. Do you see what's going on in plotting my points of the series? It is adding the next sequential term to the sum we already have. So we have traced. Now we go to our table. So to go to our table, it says to go to table set. We want our table to start at 1, and we want the change in my independent variable to be 1. We're going to hit enter, and you hit it twice. And now I can go to my table. There I am starting at 1, so 1 over 1 is 1. My next one is 2. 1 plus 1 over 2 is 1.5 or 3/2. Next one is adding 1/3 and so forth. Now, what it says there is, does this approach a value? You can just keep going down and see that my sum just keeps getting bigger. So no, it does not approach a number S, so it does not converge, it diverges. By the way, this is the harmonic series, and the harmonic series diverges. So now we start looking at series, and we want to know if series converge or diverge. We'll talk more about this in class. Our first series is the geometric series. Now we have a geometric series is of the form, n goes from 1 to infinity, my first term, times r to the n minus 1. Remember in the last lesson we talked about why it was n minus 1. That is because for the first term, I don't need to multiply by a common ratio, but for the next term I do. So I'm multiplying by n minus 1 r's to get each term. So our series diverges if your common ratio's absolute value is greater than or equal to 1, and it converges if the absolute value of r is less than 1. Now, if it converges to this sum. You should have seen that in geometry. The sum of the first n terms of a geometric series is s sub n equals the first term times 1 minus r to the n over 1 minus r. Determine whether the following series converge or diverge. Now let's look at this one. Notice that my signs are alternating. That means that r is going to have a -1 as part of its factoring. Looks like I'm multiplying by 2/3. If I multiply this by 2/3, I get 29 2/3. Okay, so it looks like my r is -2/3. Now I can find that by taking -10/3 and dividing by 5. Or I can do what I just did, which is try to establish the pattern and see if it's working. Now, the series is geometric because we have a common ratio, and that absolute value of the common ratio is less than 1, so the series converges. I can find the nth term and write it in summation form. There's my nth term formula. My sum, a sub 1 times r to the n minus 1. I could also write this starting at 0, 5 times -2/3 to the n. If we start at 0, this becomes 1. 5 times 1 does give me my first term of 5. Now I can find the sum Because this converges, I can use my infinite series. If the absolute value of r is less than 1, the sum of my series is the first term divided by 1 minus r. The first term divided by 1 minus negative 2/3, which we know to be 1 plus 2/3, which is 5/3. 5 divided by 5/3 is 5 times 3/5, which is 3. So this series will add to 3. All right, first of all, let's look at how we could write this. We could write this as the sum, as n goes from 1 to infinity, of 5 times 1/2 to the n. There's a common ratio. That common ratio's absolute value is less than 1. So we have common ratio. I can list my terms starting at 1, 1/2 times 5, times a half, times a half, times a half. Okay. So r, absolute value, is less than 1. So my series converges. I can find what the series converges to because we have a formula for a geometric series. First term, that's one reason we have to list out the terms, divided by 1 minus r, do the math, and the series will converge to 5. All right, let's look at this one. My r is 5/2. That would make my first term 5/2, my second term 25/4, my third term 125/8. Here's how I would write my general term of my sum. But notice, absolute value of r is greater than 1, so my series diverges. Oh, this one looks very, very tricky, and it is. So let's think of this as 2 to the 2n times 3 to the, let's switch that order, the opposite of n minus 1. Now we have some aloha going on here. Notice that that negative exponent is going to put this down here. Now, what does 3 to the n minus 1 mean? It means 3 to the n times 3 to the negative 1. Okay, we can do a little more work here. It would be so nice if this in the top were something to the n power, because then I would have that over 3 to the n power. Well, 2 squared is 4, so this can be written as 4 to the n. 3 to the negative 1 down here in the denominator means 3 to the 1, not in the denominator. And notice we have 4 to the n and 3 to the n. I can write that as 4/3 to the n. Now, is this geometric? Yes. A sub 1 times r. In this case, it would be to the n, and my r absolute value is greater than 1. So my series diverges. That's a repeating decimal. We know that to be 0.784784,784. If we think about what's going on and write it as a sum, 0.784 plus 0.000, 784 plus 0.000, 784. So we can see if we write that in fractions, what we're really looking at. And when we do it this way, we can see that r is 1 over 1,000, or 0.001. My absolute value of r is less than 1. So this series converges. I can find the sum. So my sum is 784 over 1,000, there's my first term, over 1 minus r, which is 784 over 1,000 over 999 over 1,000. Oh, the thousands cancel. There's my sum. This is why repeating decimals are rational, because we can write the sum as a rational number, a fraction. Properties of infinite series. If the sum as n goes from 1 to infinity of a sequence a sub n is a, and the sum as n goes from 1 to infinity of another sequence b sub n is b, and c is a real number, I can multiply every term in the sequence by that c, and my sum would be c times the sum of my series. I can add the two series together, and I can subtract them. So sometimes we have to manipulate our series. So these are good properties to know. the limit of the nth term of a convergent series. If a series converges, then the nth term is getting very, very close to zero. That does not mean if the nth term is getting close to zero, the series converges. If P then Q is true, does not mean if Q then P is true. Okay? No. All right? So if we know the series converges, then the limit of the nth term is zero. Very important. Now, we have something called the contrapositive. If we know if P then Q is true, then we know if not Q, then not P is true. So let's look at this one. We know if a series converges, then its nth term, the limit is zero. So the contrapositive would say if the limit of the nth term is not zero, then the series does not converge. In other words, if the limit as n goes to infinity of the nth term is not zero, then the series diverges. This is called the nth term test for divergence. It only tests for divergence. It does not test for convergence. Notice how many times I have written this. If the limit of the nth term goes to zero, that doesn't tell us anything. We're going to need to use another test. And so we'll start with the very first series we looked at, our harmonic series. The nth term was zero, but we looked on the calculator and saw it never approached, the series never approached a sum. It diverged. So we're going to determine whether the following series converge or diverge. The nth term says if the limit of the nth term is not zero, the series diverges, the nth term test. So my limit of my nth term is not zero. So this series diverges by the nth term test. Now a question you may be asking, do we have to write all this? Yes, you have to write exactly what I am showing. That is not an optional. You have to write out the work and you have to write your conclusion, just like this. Oh goodness, we have to look at factorials. How in the world do I work with that? When we have a factorial situation, we are going to divide every term of my ratio by n factorial in this case. When we do that, we get 1 on top, 3 minus 1 over n factorial. Now, what do we know as n goes to infinity? This is going to get bigger and bigger and bigger. So 1 over that is going to get close to 0. So my limit, you should see, is 1/3. Limit is not 0, so my series diverges by the nth term test. Notice I wrote here, L'Hopital's rule does not work. We can't take derivative of factorial. All right, let's look at this one. Well, it's not really geometric because I got other stuff going on here, but let's divide it into two ratios. So I can now look at the limit. This is going to be how we get that nth term. A sub n is all of this. Okay. And we can see that this becomes 1 minus 2 over 3 to the n. This is 2 times 1/3 to the n. Now, this is, as n goes to infinity, 1 minus 0, which is not 0. So this series is going to diverge by the nth term test. Notice that this series is not geometric. If n is 1, I get 1 minus 2/3, which is 1/3. If n is 2, I get 1 minus 2 over 9, which is 7/9. If n is 3, I get 1 minus 2 over 27, which is 25 over 27. Notice I am not multiplying by a common ratio to get the next term. Now we have a special series here. We're going to show that this series is convergent and find its sum. Well, we can see we can do a partial fraction decomposition, and we can get that this becomes this. Don't forget, we had this process from our partial fraction decomposition. Take a moment to write this down if you wish. So now we're going to look at our sum as I goes from 1 to n of replacing these n's with i's, and we know that this became this. And look at what happens. When I is 1, I get 1 minus 1/2 plus, when I is 2, 1/2 minus 1/3 plus, when I is 3, 1/3 minus 1/4, all the way up to my nth term. Do you see what's happening? Minus 1/2 plus 1/2, minus 1/3 plus 1/3, minus 1/4, and so forth. So this series becomes this. It collapses to that. So now let's look at the limit of my series, okay, which is, I'm not looking at the nth term, the limit of my series. The limit as n goes to infinity of 1 minus 1 over n, which is 1. So we say this series converges by the telescoping series test. A series such as the one above is called the telescoping series because it collapses to one term or a few terms. If a series collapses to a finite sum, then it converges by the telescoping series test. And this example, if we take this series and list a few terms out, you can see what's going to happen, and we are going to converge to 1 by the telescoping series test because we'll have 1 minus a very, very small number. So go ahead and write this example down. Show that the harmonic series diverges. That would be the sum as n goes from 1 to infinity of 1 over n. That would be 1 plus 1/2 plus 1/3 plus 1/4, blah, blah, blah. Show that it diverges. Now what we can see is the nth term has a limit of 0. Jake Bernoulli is the mathematician who did this proof. So our nth term goes to 0, but our series diverges. We will do this in class. Go ahead and write this down, though, so it's ready to go. Your TPs for this section: 3, 13, 25, 35, and 51. See you next time.